Thank you very much for coming. I was warned, so many meetings are going on, but I'm glad many people are came. So today speaker is Tse-Chun Chen. Tse-Chun Chen. He's a student of Eugenia, and he's taking over the work of Otta-san and Hotta-san, Daisuke, and he's continuing to developing. So it's related to our operation. And he graduated from National Taiwan University in atmospheric science, and he started working with Eugenia since 2013. Thank you very much.
I'm using this one?
Yeah, that's okay.
Right. Hello, everyone. I'm Tse-Chun Chen. Thanks for coming to this talk. So today I'll be talking about the efficient estimation of the impact of the observing system using EFSO, and I'll explain EFSO a little bit later for those people who are not familiar with that. So I would like to take some time to acknowledge people who have helped in this project. Can I use this one?
Okay.
I prefer to press the arrow key.
Okay. Sorry. We need a longer cable.
Oh, I'll just use the mouse. Okay, so the objective of this project is mainly to handle the massive amount of observations. So as we all know that there are more than a millions of observations being assimilated in the model every 6 hours. And the graphs I'm showing here are the examples that are simulated in my experiments. So the top one is satellite radiances, and the bottom one is non-radiance observing systems. And so there are already a lot of them. And thanks to the advance of technology, there are more on the way. So for example, the next generation geostationary satellite, like the GOES and the Himari series, and also the phased array radar. So both United States and Japan have those. So compared to the older version, these new systems generate 15 times more data. So these are all very good, but the real question is that how do we efficiently evaluate the impact of them? Okay, so speaking of evaluating the impact, the first thing coming into mind is the OSSI. So the OSSI compares so you have two runs, one with a set of observations and the other without the observations. And you compare the two at the 5-day forecast, and then you'll know how these observations harm or improve the forecast. But the problem is that the discernibility is low. If you use OSSI, you need to create an additional run in order to assess the impact of one set of observation, and it's computationally expensive. So to resolve this issue, Lang and Becker developed the forecast sensitivity to observations to provide a method that is computationally efficient to evaluate the observation impacts. But the problem is that it requires an adjoint model. So in a report from ECMWF, they reported that there are inconsistency in representing the moist process in their adjoint model. And then Eugenia in 2012 formulated the Ensemble version of FSO, which we call the EFSO. So it also can efficiently evaluate the impact of each observation. And it's free of a joint model because it uses ensembles. But the problem is that it requires a special treatment in localization. So here's the formulation of EFSO. So the concept is that when you have a forecast starting from 6 hours earlier, and then you assimilate your data at this time. So the only difference between the forecast, and we verify the forecast at this time t, it can be any time. So the only difference between the forecast, between the two forecasts, is that you assimilate these observations here. So what EFSO does is that it projects the forecast error changes from this verification time back to this time, the observation time, and then attribute to each individual observation. So that's how it evaluate the impact of observation efficiently. So the negative values of EFSO means that the forecast error is reduced by the observation, so it's a beneficial observation. But if the EFSO value is positive, then it means that the forecast error grows because of assimilating it. So we call it detrimental. I want to emphasize that detrimental doesn't always mean flawed. It can be a perfect good observation that it harms the forecast. We'll talk more about that later. So the experimental setup, I run a 1 month experiment using GFS T254 for the deterministic forecast and T126 for the ensemble forecast. For the data simulation system, we use LATKF 3-bar hybrid GSI with an older version, 2012. And the localization cutoff length is 2,000 kilometers. And two scale heights, and the error norm we're using is the moist total energy. So it includes kinetic energy, internal energy, potential energy, and latent heat. So this is one example of the EFSO diagnostics. So this is on 2012 February 16th 18Z. So the first impression for people who are not familiar with EFSO, the first impression would be there are so many detrimental observations. So let me clarify that. So the color scheme here, the positive means the red means positive, and it means detrimental observations, and the blue means it's beneficial observations. So you can see that the blue and reds kind of mix around, and the average rate of the detrimental observations is about 50. It's about 50%, a little bit less than 50%. So if you average these impacts region by region, then you'll get the net impact is beneficial impact, except for the two regions I marked with a black box. So in the black box, you can see that they are clustered with red, the detrimental observations. So these observations are provided majorly from the MODIS polar wind, and we'll talk more on that. So another view of EFSO is, so this is showing the time evolution of the total impact of each observing system. So you can see that so down here the negative ones are the beneficial observing systems, and up there is the detrimental impact. And you can see that the top three observing systems are the aircraft, the GPS RO, and the radio sounds. It's interesting. You can see that in the radio sounds, you can see this kind of zigzag, and that's because of that most stations release their sounds every 12 hours. So most of the observing systems stay down here, but you can see that there are several other systems that continues to provide these what we call the detrimental episodes. So these I marked in the red boxes on the labels. So it includes Atlas buoy, drop sounds, MODIS winds, next red winds, Pibel, and profiler winds. And among them, modus wind seems to.
This box.
Oh, okay, thank you. So among them, modus wind seems to contribute a lot of the detrimental episodes, and also the magnitude of the detrimental impact is larger. Yeah, so from this, just looking at this application, we can see how EFSO could be very useful in identifying those observing systems that provides these kind of detrimental episodes, and just to monitor the quality of simulating these observing systems. Yeah, so we decide to look investigate further the modus winds. So and then we discover these kind of biases. So in the modus winds, we found that the detrimental modus winds tends to occur with dependence of the innovation, the sign of innovation, and the observed wind directions. So, for example, here in the red we show the detrimental impact, and the blue again is the beneficial observations. So we divide them into, like, the modus winds. There are three types of them. There are cloud track winds, water vapor tracking winds in a cloudy sky, water vapor tracking wind in a clear sky. And we divide them into the U component, V component, and both on each hemisphere. So we can see that there's a we first discovered these kind of innovation bias. We noticed that there's a prevailing positive innovation bias in the U component in general. And then we found that these innovation bias actually depends heavily on the wind directions. For example, take this one for example. You can see from the westward wind, the detrimental observation tends to happen when the innovation is positive, where at the other, like here in the V component and the poleward wind, you can see that the relation is reversed. So, and also an interesting thing is that you can see for the cloud track, the cloud tracking winds and the water vapor tracking wind in clear sky, they look pretty similar to each other. Well, it's not the same for the water vapor tracking wind in a cloudy sky. So that says that there must be something in common of the cloud tracking winds and the water vapor tracking winds in clear sky, where that common thing doesn't share with the water vapor tracking wind in cloudy sky. So this could help us to improve the observation product. We are now collaborating with the modus wind experts in Wisconsin in order to find out what is the root cause of this. And also, I want to say that it is this graph alone is very good for just a fixed state-dependent QC. But there's a trade-off if you just want to apply this for a fixed QC, because you need to find the right variable, and also it sacrifices some of the flow dependency. So in order, we also look at the geostationary satellite winds, which use essentially the same algorithm, and there are no such kind of bias in it. So to fully account for the full flow dependency, we use the proactive quality control algorithm. So the algorithm is that, so we have a normal data assimilation cycle where we start from here. We have an analysis and we make forecasts, and then we obtain we obtain the observations here and make the analysis again, and then the forecast. So suppose that we want to do EFSO and PQC at this time here. Then we wait until the next analysis becomes available so that we can do EFSO. And then from EFSO, we can determine which observations to be rejected at this time. And then we remake the analysis again. And the analysis is improved by rejecting some of the detrimental observations, and the subsequent forecast is improved. So we are going to introduce three data denial methods. So the first one is actually pioneered by Hotta and Oda. And at the time, they add some restrictions on doing PQC because they are being careful and more conservative. So they first identified areas with forecast error degradation. So it's marked with the black box here. So this is just one of the cases. So then they perform EFSO with respect to these forecast degradation regions. And then they reject only the detrimental observations that it comes from the observing system that has a net detrimental impact. So these dots are the rejected observations in these cases. So that's including the modus winds and some of the aircrafts. And yeah. So we can see how the forecast improved by rejecting those detrimental observations. So we can see the blue here means that the forecast error is improved. So here we can see that the changes, that the improvement first located, in the beginning it locates near where we reject those observations. And we have a slight degradation here, but it goes away really quickly. So we can see that these improvement actually grows in time and also propagate with a weather system at a later time. And it continues to grow until like 3 to 4 days later, and then started to decay. But the improvement, you can see it remains until, remains beyond 5 days. So the other two, we are, so that was very promising. So we want to try something that's more aggressive. And so that's the threshold method and the beneficial growing mode. So in the threshold method, I simply compute the global EFSO. I do not restrict them to the forecast error degradation region. I compute the global EFSO, and I reject the detrimental observations that is larger. It's more detrimental than a threshold of 10 to the -5 joule per kilogram here. So that's the threshold. And by doing this, I'm rejecting these observations here. This is an example from one of the cases. And I'm doing this only to the non-radiance observations. So there are 7% of non-radiance observations being rejected in this method, in this case. So the next one is a pretty interesting one, is the beneficial growing mode. It's not going to be affordable in operation, but it's good for reanalysis. So this is inspired by Anna Trevisen's assimilation in unstable subspace. So what we do here is that we compute 6-hour EFSO and 24-hour EFSO. So we have 2 time steps here. And we assimilate only the observations that is beneficial in the 6-hour and becomes more beneficial in the 24 hours. And the resulting, the rejecting observations are shown here. And we can see that, so the colors here are for the 6-hour EFSO. So we can see that a lot of observations that were beneficial in the beginning are getting rejected. And by rejecting them, we can see that the forecast actually improved. So that's 50% of the non-radiance observations. So we compare the 3 methods here. And so from the top row, we can see Hotta's method improves on. So this is an average for 18 cases. So for Hotta's method, we can see the improvement at 5 days is around like 0.5%. But the threshold method, you can see on the global average on the fifth day, you can see that's around 3%. And then the beneficial growing mode, we can see that on the fifth day it's around 5%. So this is verifying against the control analysis. And then we also can compute the geopotential height at 500 hectopascal with the ACC score and verified with the EC interim. And we can see that for the global average, the threshold method improves the forecast, and the beneficial growing mode improves the forecast even further. So that's, sorry, I should have mentioned this, that these are offline experiments, which means that the improved analysis is not used as an initial condition for the next forecast. But so we tested in a cycling fashion that we performed 40 cycles with the threshold method. So we compare the improvement of offline threshold method and the cycling threshold method. And we can see that, so the red is the cycling method. So we can see that on global average, the cycling method outperforms the offline method. The cycling experiment, the cycling forecast outperformed the offline forecast, and it maximized around 3 to 5 days. And this, the reason of this is that the benefits of PQC keeps accumulate in each cycles, and so it benefits from the past beneficial effect of PQC. So now we are going to discuss the feasibility of implementing PQC in operation. So the first question to answer is that is it necessary to redo the analysis again because it's very computationally expensive? So Hotta provided a formulation to do the approximation. So in this approximation, we are assuming that the Kalman gain K doesn't change so much, but because it's actually depending on what observations you are assimilating. But we're assuming that the K remains constant. So we can compute the K with the ensemble perturbations, and then do the approximation. And we can see that we're comparing here the true correction, which we redo the analysis again, and the estimated correction. And we can see that the patterns are very similar, and the correlation is very high with some overestimation. And the reason for the overestimation, we think, is that because we're using a hybrid system, and there are only 75% of the background that's coming from the ensemble part. So to fit PQC in the NCEP dual track analysis, we put so here we put the PQC here right after the GDAS analysis. Right after GDAS, actually right after the early analysis is done, which is so in this example we're doing PQC for the 0Z, and we need the 6Z analysis to do the verification. So if we make use of the early analysis, then we can save actually 3 hours of waiting. So we don't need to wait for this one. We can actually just wait for this one. So this is done by like 9/16, and and so that leaves us a 2.5-hour windows here to do to do PQC here. So if we want to implement this in operation, you'll see that there's no way that, because we need the future analysis to do the verification, so there's no way that the real-time GFS forecast to benefit directly from recent PQC. There's always a 12 hours delay here. Okay, but it can actually get benefit from the accumulation of PQC over the each past cycles. So we want to mention that we're collaborating with the forecast scale dropout team with Jordan and Krishna. So they found that some GFS forecast dropout cases are actually due to the detrimental observations, and they found that some of the detrimental observations are the contaminated radiances. So we think that EFSO or PQC can help identify these contaminated or irradiance or the detrimental observation that causes the dropout case. So this is a brief summary. So we've shown that EFSO is very efficient in estimating the impact of each observation. So it can you can use it as an online monitoring tool for the impact of each observation. And we also show that PQC threshold for operation it improved the analysis and the subsequent forecast up to 5 days, and the beneficial growing mode, which is affordable in reanalysis, can improve further. And we also proved that the almost no-cost PQC approximation it's quite accurate compared to the true correction. So now I'm going to switch from the real world to an idealized system to show you some recent results. So the experiment setup is we're using the Lorenz 96 40-variable model, and the forcing term is 8. We're using Ranchikuda 4 with 5,000 cycles, and we are using ETKF for 40 members. And all of the grid points are being observed. So this is a remake of what Eugenia have shown before. So in the first case, we intentionally add large random errors. So the random errors add to the observations at grid point number 10 is 8 times larger than specified in R. And we can see that by averaging the EFSO impact, the EFSO could identify these flawed observations. And one interesting thing is that because this is flawed, so the neighboring observations are being more helpful. So the other case is a bias observation. So we add a constant bias at grid point number 30, and we can see that EFSO can also tell. So this is showing that EFSO could truly identify flawed observations. So here we offer an explanation of the low percentage of beneficial observations. So in the literature, they attribute these low beneficial rate to the incorrect verifying analysis, or it's just the statistical nature of data assimilation, or incorrect assignment of B, or the modes with different growing rate. But our finding is that it is actually because that our background is very accurate. So here what I'm doing is that in the system, I adjust the assimilation window from assimilating every time we do a forecast to every 100 times we do a forecast. So by adjusting the assimilation window, we are actually varying the quality of the background. So we can see as the background goes bad, which is here, the beneficial rate increases to 90%. So that's saying that if your forecast is accurate enough, then there's not so much information you can get from the observations. But if your forecast is so bad, then then almost all the observations are very beneficial. And we also do the same thing for the observational error. We can see that as the observations become more accurate, which is here, the beneficial rate increases as well. So our explanation is that our forecasts are doing a very good job here. So this is another interesting thing. I want to mention that I get this idea from Kozuki at RIKEM. So here we are showing that how the forecast error and the subsequent the analysis error and the subsequent forecast error changes with the number of rejected observations. So we start here the 0 means that we reject no observations, and here 40 means that reject every observation. So this is the first one is the single cycle PQC, and we can view it from a different point. So this thin black line is the error of the background. So when you start to assimilate one observation, the analysis error decreases. And as you assimilate more observations, the error of analysis keeps decreasing. But up to some point, it saturates. Like no matter how much observations you assimilate, like around here in the middle, no matter how much observation you assimilate, the forecast error doesn't decrease further. And at the end, if you assimilate these detrimental observations here, then your analysis error increases again. So if you do the forecast from these analyses, you can see this kind of U shape keeps going in the future up to beyond 15 steps of the forecast. So here we show that the impact of PQC remains up to 15 steps of forecast and reject some of these detrimental observation. Actually improves the analysis here. So this is for just one cycle. So if we do a cycling PQC, which is like 5,000 cycles, we can see that. So here the horizontal axis is the percentile. So from here, it's around 100 here. On the right is rejecting all the observations, and here I'm. So yeah, so you can see that at around if we reject like 10% of the detrimental observations, we get a maximum improvement from PQC. And what happened? So the take-home message here is that these seems to be an important improvement by assimilating these observations, but these small initial error could actually grow in the future. So that's why that we don't have this kind of flat bottom structure at the cycling PQC here. So so reject 10% of detrimental observation over cycles gives you the best result here. So here we're demonstrating that. So in this experiment, there are no added flawed observations. So we're showing that PQC even works without flawed observations. So a brief summary. So we offer an explanation of the low beneficial rate. So that's because our forecast is very accurate, and EFSO detects the flawed observations, and that PQC works even if there are no flawed observation because EFSO can identify the detrimental observations that's harmful for the forecast. So future directions that continue investigating the cause of detrimental modest winds, and to use EFSO to help doing QC in the radiance observations, like the satellite, the channel selections. And also expand PQC to reject the radiance observations, and also explore the connection between PQC and the simulation in unstable subspace. Thank you.
Any questions?
Can you explain the formula at the beginning? How does this work? Sorry, the beginning.
Yeah.
How do you know this attribute to different observation type? How does this work?
So you can see in the formulation here.
I am glad that she didn't ask me.
Oh. Yeah. So you can see here is the forecast error in the future, and so the C here is just the error norm we're using. So you can pretend it's not there, but you can use any norms. But so the norm we use is the moist total energy. So the forecast error here is projected by these ensemble information here. So this is the forecast perturbation, and this is the analysis forecast perturbation. Analysis perturbation at observation space. So if you multiply the two and multiply this one, then you actually are projecting the forecast error from the future back to the observation time. So and to the observation space. And how we can do to evaluate the individual impact of the observations is that we don't. So this is a vectors of the innovations of each observations. So if we don't don't do the multiplications of the whole list, we just pick one at a time, then you'll get the individual estimation.
It's very similar to the adjoint, the FSO, but it's much simpler to compute because everything is available from the ensemble, from the data simulation, so you don't need to compute these things.
So, going back to your earlier slide on Modis, you seem to be saying that you have this difference between the positive innovations and the negative innovations, causing improvement or degradation to the forecast. And you're assuming you seem to be assuming it's the modus observation itself that's wrong. Now, is there a possibility that it's actually something to do with a sort of model bias?
Yeah, possible. That's possible.
So, but then, I was always taught when I was learning this stuff that if it's a model bias, we shouldn't be addressing it through DA. We should be just telling model people about it. I'm just wondering if addressing this through QC is a good short-term strategy, but you still need to look at the detailed causes of actually what the problem is.
Yeah, of course, I agree with you. So we think that PQC or EFSO could at least solve the problem in the short term until you fix the problem, the bigger problem. Yeah, I agree with you.
I apologize if this was when I was out of the room. We covered this. Could you go back to the timing and the application in operations?
Sure.
Yeah, that little thing there.
Yeah.
Okay. So you do a forecast up to 6Z. Use the difference in between. Okay, could you run through how it would work in operations?
Yeah. Yeah. So essentially, we're trying to use PQC to correct this analysis. So it's the 0Z. So in order to do PQC, we need the 06Z analysis in order to do EFSO and PQC. So normally we would think that this is the next available analysis, but I think it's actually your suggestion to not wait for the final analysis here, but just make use of the early analysis here as verification.
Actually, that was your idea when
Yeah.
we talked.
Well, I know, but I'm not sure I understand it.
Oh. Yeah, so until this is available, then we can perform EFSO and then do PQC. So PQC is doing it's here, and then it makes we make forecasts from the PQC corrected analysis to be make the forecast and do the beneficial impact will pass on to this final analysis here.
Okay, so you're doing an additional, I'm trying to see what you're adding to the cost of the cycle.
Yeah.
You would be adding an additional 6-hour forecast
Yep.
To the cycle, and
But only determinate forecasts. We can reuse the ensemble forecast that's performed before. But anyway,
right,
yeah.
right.
And also this one here. So we can either redo the analysis or use the approximation to do it.
Actually, the ensemble bit gets complicated because we recentered the ensemble about the late GDAS analysis.
Uh-huh.
So if we're correcting that, we will have to account for that in the ensemble as well.
Can you say it again?
When we run a hybrid, we replace the E and KF state estimate with the hybrid analysis through a recentering procedure. So if we're going back and recorrecting the late cycle GDAS analysis through PQC, we probably have to account for that in the ensemble as well.
But I thought you can just save those ensemble information. It's
not linear. We're restarting from different places in the initial condition. It's something you have to think about and look at.
Mm-hmm.
Thank you.
I'm sure I didn't completely follow what you said, so I'll ask you later. But Hotta found that the results, that the identification of the detrimental observations was quite robust with respect to which analysis was used. So it didn't matter if you used just the late EKF or the 3D bar or the hybrid. So in that sense, the identifications of the flow of the detrimental observation seems to be robust, but you're probably right. And I have to say, you were the one that pointed out that we won't get the forecast in real time, but 12 hours later. But fortunately, the benefits from previous PQCs are still. So it was very helpful that we didn't think of that, but it's still, as he showed in the cycle experiments, the benefits accumulate and are maximum from the past after 2 or 3 days and up to 5 days. Sorry, I'm just being defensive. But thank you very much for that comment. I thought maybe you could point out that even if you don't use it for anything else, you can still use it to, if you have a new observing system, you can compute, well, like this shows, it gives you a day-to-day ability to see what each observation is doing and whether it's bad. But also Lien's.
Oh, yeah, sure.
Yeah, this is kind of complicated, but why don't you explain?
Oh, sure. So, so for the fixed QC I mentioned about for the modus winds, actually Lien did something with a similar idea. So at the time he was trying to effectively assimilate the precipitation, and by doing so, if he assimilate, so he found a way by doing a Gaussian transformation, and if he found that if he assimilate all the precipitation data, then he gets this kind of improvement up here, the first one here. And by trial and error, he found that the improvement actually depends on, so he can do data selection with the precipitating members. So he found by trial and error that 24 member is kind of a magic number for his experiment. So if he limits to the assimilating of precipitation to the members, the precipitate members that is larger than 24, then he gets the blue curve here, further improvement. And then he performed EFSO to confirm that. So let's just focus on the top row here. So the left one is for the observation that is larger than 0, and the 0 precipitation here on the right. So you can see that for observations larger than 0, it is beneficial no matter how many precipitating members you have in Ensemble. But for the 0 precipitation, you can see that actually depends how beneficial are these observations depends on the precipitating members here. And you can see that only around 24 or something here, you can see that the 0 precipitation is beneficial, but if your precipitating member is not enough, then the observations are harmful to your forecast. So when he applied this additional rule, which is the extra check here, it actually improves the forecast even further. And yeah.
Yeah. In a more general way, suppose that you have a new observing system and you have no idea what kind of quality control to apply. Then you get all this information from EFSO, and then you can choose what EFSO said are the bad observations and just filter them out from do a quality control, and that's what he did there. And it took him like a year before he did it without EFSO, but when he got EFSO, immediately he saw that he could still improve it by just getting the quality control from EFSO for a large number of cases.
Yeah, as I mentioned before, the 24-member threshold is due by trial and error. He done a lot of experiments in order to get that 24 threshold. But with EFSO, you can see that he can immediately get that 24 or 20 something just from EFSO and just one experiment instead of a lot.
So it's good for new observing systems to do quality control.
Could there be any advantages in replacing the binary accept and reject?
Yeah,
style with something where you have a graduated weighting of the dubious observations. Because sometimes you can never be sure whether they're really bad observations.
Yeah, like you did.
Yeah, like QC does.
Yeah.
See, you can do something about that. Also, maybe Eugenia would not agree on me with that. So in PQC, we reject the whole observation if we think that's the detrimental ones. But I think that maybe there's a more gradual way to do that, that we don't reject it at all, or we reject percentage. So essentially what's changed in the code is that I reduce the innovation of that detrimental observation.
Well, you reduce the weight that you give it.
Yeah, you can explain it in the weights or of innovation, either way.
It might be worth trying.
Yeah.
I don't think for some of these observations you can be sure that it's a bad observation.
So
Yeah, they're not really bad. It's just harmful to the forecast. It's not the quality.
It might be less harmful if you just down-weighted a bit.
Mhm.
It may have certain aspects to it that are improving some components of the forecast and making a detrimental effect on others.
Yeah, yeah. So less radical way of rejecting it can be applied. Yes.
Any question from telephone online?
Yeah, this is Ron Gelaro. I have a question.
Yeah.
Yeah, so I appreciate the results, and but it's just philosophically, I mean, it's sort of what Jim was saying, and even maybe what Andrew was saying before, follow on. I think that was Jim I just heard.
Yes.
I mean, in principle, I still always struggle with the idea that, you know, based on this one metric, you're throwing out a lot of what are likely to be good observations that you're handling the wrong way based on a single instance, and this, you know, it's not even a statistical, a month worth of these things. It's that tell you a certain data type's performing well. It's a single instance. You know, we know it's subject to a lot more things than just the quality of the ob. I don't know if you've ever redone the calculation after you've removed those obs for that analysis and that forecast, but my suspicion is you'll get, you know, another batch that kind of has about the same quantity of quote-unquote detrimental obs. So it's the philosophy of throwing out good information based on this one metric that could otherwise, as Jim was saying, be doing lots of things to the quality of the analysis that, you know, are probably quite good. So you know, from the very beginning when we started working with this stuff and saw this potential, that was always kind of a, you know, a psychological roadblock for us. So, you know, how do you deal with that suspicion that you're probably throwing out a lot of good quality information?
Well, so maybe. So from this slides, actually, you can see that one instance of EFSO would tell you that assimilating these observations here doesn't help much in this analysis. But by a cycling experiment, we can see that those observations are actually very helpful in some way in the future, providing helpful information here. So it's not as so this is about 10% of the detrimental observations that gives us the best performance of PQC. It's not as radical as like 50% in the beneficial GORMO I showed before. And also I would like to mention, so this may not be a direct answer to your questions. So here I'm trying to explain what EFSO is truly measuring. Suppose you have an analysis here, starting from this time here, and then you do forecast. And then you have the red circle is the sort of like the distribution of the observations with a center at the stars. So the true state is here indicated by this line. So assimilating these observations get your analysis closer to the true state, but it's not like on the true state. But so anyway, so when you make a forecast here, and then so what EFSO truly measure is that if the observation you assimilated is pulling your background towards the true state here. So so if you compute EFSO in this case, then you will immediately found that all the detrimental observations are actually these ones larger than your background, and these observations down here smaller than your background. It's pulling your future forecast towards the true state. So these observations down here are quantified as beneficial in EFSO, but you can see that it doesn't really means about it. It doesn't really care about the quality of the observation itself, because you can have a lot of outliers actually down here, which is quantified by EFSO as very beneficial observations.
Yeah. Yeah.
So when we do PQC, actually rejecting all the detrimental observation is not a good idea, because we sort of rely on the balance between these ones up here and these ones down here to get to the true state. So what we want to do is just gradually remove part of these up here in order to get an improvement in forecast.
Mm-hmm. Yeah, I understand what you're saying. Can I just, if I could have the floor for few more seconds? Just a jargon comment. I think if you want to stick the E in front of this, that's for Ensemble, that's fine, and it's sort of accepted now, I suppose. But this isn't really forecast sensitivity to observations, right? That's not what this is. So the community is kind of moving away from that, and it's really, it's an observation impact calculation. This is not a sensitivity calculation. So it'd probably be, most of what you'll see now in the print is FSOI, to acknowledge that it's forecast sensitivity observation impact. Because the forecast sensitivity to observations is a gradient calculation, which is not what this is. So I would just recommend, as a sort of an editorial comment here, that you put the FSOI nomenclature. It's just a lot clearer now on what you're discussing.
Okay, thank you. Thanks for
Sure.
clearing out.
I just want to make a comment. In your calculations that you have done with mostly the conventional, quote-unquote conventional in the operational sense here, using the prep buffer file.
Mm-hmm.
And what we are, the dropout team and Eugenia's team, what we are trying to accomplish is to extend this for the radiance calculations for some of the dropout cases, so that we can understand the ramifications of the proactive QC in terms of the degraded observations and rejecting the degraded observations found from the EFSOI and its relation to the alleviation of the dropouts. So that would be very interesting, that we are trying to to collaborate in our this
Thank you.
effort. So I just want to mention that.
Thank you.
I was wondering if we could get together and talk about that right after the meeting. And it's almost, it's one.
Okay.
Yeah.
Are you going to impact stable with respect to time for each instrument type or station? Are you going to impact for stable with respect to time for every instrument or station?
You're saying is the occurrence of detrimental observation stick to one station?
Yeah, can you use it for a blacklist, for example? The stable.
Change it. Sorry.
I think It's asking if the detrimental impacts of one observation, one type of observation is stationary through time. It's always bad. Sometimes it's good, sometimes it's bad.
We don't find that in the GFS experiment, because if that's true, then you probably would reject it already by other kind of QC, right? So the sorry. So maybe for this one, yeah. So this is the average total impact of all the the non-radiance observation systems. In my experiment, you can see that they are all beneficial, like in general. I mean, on average, the overall is beneficial. But like, take Mortis winds, for example. You can see the standard deviation sometimes extends to, it's just occasionally that it extends to the detrimental part.
Okay. Any more questions from online? Okay. Thank you very much for. Yeah, that's right.
Thank you.
Yeah. I should get the extension for this one.
Oh.
Yeah.
You made it to the end.